Bridges are some of the most trusted structures in the world. We cross them every day without stopping to think. Cars move. People walk. Trains pass overhead. But beneath that simple movement is an incredible balance of math and engineering that makes sure everything stays exactly where it should. Every bridge begins long before construction ever starts. Engineers first study the land. They look at the distance that needs to be crossed, the type of soil below, and the forces the bridge will face for decades. Gravity is constant, but traffic changes. Wind pushes. Temperatures rise and fall. Earth can shift. The goal is not to eliminate these forces. It is to control them. At the heart of every bridge are two opposing ideas: compression and tension. Compression pushes materials together. Tension pulls them apart. A safe bridge carefully balances both at the same time. If compression becomes too great, materials can crack or crush. If tension becomes too strong, cables or beams can stretch or snap. This balance is guided by math. Engineers calculate the weight of the bridge itself, called the dead load. Then they calculate the live load, which includes vehicles, people, wind, rain, and snow. These numbers are never guessed. They are measured, modeled, and multiplied with safety margins that account for the unexpected. A bridge is always designed to hold far more weight than it will ever experience. That extra capacity is what keeps structures standing during heavy traffic or extreme weather. Shape plays a huge role as well. Geometry is not just visual. It is structural. Triangles are used because they do not easily change shape. Arches are used because they push weight outward instead of straight down. Suspension bridges use long curved cables that naturally distribute tension across great distances. Every angle, curve, and joint is calculated to move force in a controlled direction. Nothing is random. Materials are chosen with the same level of care. Steel is excellent at handling tension. Concrete is strongest under compression. Together, they form a system where each material supports the other. Engineers study how these materials stretch, bend, and age. They calculate how metal reacts to heat and how concrete responds to years of stress. They also consider fatigue, which is the slow weakening that happens after millions of tiny movements. A bridge is not built to survive one day. It is built to survive millions. Even the smallest details matter. Expansion joints allow the bridge to grow and shrink with temperature changes. Bearings allow controlled movement during wind or earthquakes. Drainage prevents water from weakening the structure over time. Before construction begins, everything is tested digitally. Computer models simulate decades of use in minutes. Engineers apply loads, simulate storms, and push designs to their limits before a single beam is placed. Only when the math proves reliable does construction begin. What makes bridges so fascinating is not just their size or beauty. It is the quiet precision behind them. Thousands of calculations working together so that millions of people can cross safely without ever noticing. Every bridge is a conversation between math, materials, and motion. A structure that holds still while the world moves across it. And the next time you cross one, you are not just passing over steel and concrete. You are passing over decades of engineering, calculation, and trust.